Okay, cool. So, going to jump over into some ANOVA stuff. Going to talk about the conceptual basis of multiple means testing today, talking about how we go through and partition variability within and across means. Um, uh, this will give you a strong conceptual understanding of kind of what we're doing with here. We're going to go through some ANOVA calculations, just how to go through it by hand. We'll talk about effect sizes, confidence intervals, and the follow-up tests. We won't get that until next week, but that's where we're headed with this. Okay. So up to this point, covered a number of different means-based tests. We talked about our single sample Z. Okay. Our single sample Z, this is where we're going to be working with a mean with an analysis, testing a sample mean against some value, some reference values with known means and standard deviations. Okay. But we often don't know population means and standard deviations. And if we don't know population means and standard deviations, we can't use a Z-test. So we could transition into our single sample t-test, right? Single sample t is where I'm comparing a single sample to some known reference mean or some population mean where the population variance isn't, or the population standard deviation isn't known. And in this case, what I do is I use the sample standard deviation as an estimate of the population standard deviation, okay? But sometimes we're not testing my sample against some reference value. Sometimes I'm interested in looking at samples from two different populations. This is where I get my independent sample t-test. Okay, here we've pulled samples from two different populations that we've hypothesized are going to differ on some outcome, and we're just going to go through and see, does the difference that we see across these two samples in whatever we're measuring, does the difference we see exceed what we would expect if they were drawn from populations with equal means? Okay, gives us another tool. And last is our paired sample test. Here we're going to look at the mean difference across two assessment points with just one sample. So we've got some folks, and we're going to observe them under this condition. Then we're going to go through and observe them under a different condition and see if we see changes. Right now, generally we're thinking about one single sample, one single group of individuals. Again, that asterisk there is to recognize that we can use single or paired sample analyses or formula if I'm using a matched pairs design, but for the most part it's going to be I have one group of people and I'm going to test them across multiple assessments. Okay, so this is where we've gotten up to this point, but the issue is where these start to become limited is what if we want to compare more than two means? Okay, what if I'm doing a study, I've got drug A, B, and C, and I want to see if these three groups are different from one another, okay? Or I've got condition 1, 2, and 3, right? And for my study, it's important for me to know whether or not these three sort of some mean value looks to be different in these respective populations, right? Now, if I were to go through and use an independent sample t-test, because can only use two samples in our independent samples t, that gives me three separate tests. I've got A versus B, B versus C, A versus C. So I could go through and run all those independently and start to try and pull some information from there, right? But if I don't want to do that, if I want to kind of run this all up, because at the heart of my question is whether or not there are overall differences across these individual or across these, or if we have evidence of differences across these populations, my solution is our analysis of variance models. Okay, our ANOVA models are used to look at differences between two or more groups on some continuous dependent variable. Now, I say two or more groups. Technically, we use ANOVA generally we use ANOVA or C-ANOVA for three or more comparison across three or more groups, but we can use it for two. Really, our independent sample t-test is just a special case of ANOVA. So you can run an ANOVA with two groups. It just gives you a different statistic. They're mathematically equivalent. But in general, what we're usually looking at this is in situations where we've got three or more groups. And so the benefits, or potential benefits of an ANOVA model is that it's more efficient than running multiple t-tests, right? I can kind of look at overall, am I seeing differences? It avoids some complications with some type 1 error, okay? Natalie, can you remind me what type 1 error is? Yes. No, you're perfect. Yeah, I had to think about it in my head too. Yeah, rejecting the null when I shouldn't. The null is true. I'm claiming it. Type 1 error is I'm claiming an effect when there's not one, right? It's the big one that we're always probably or inordinately concerned with in at least psychological science. But yeah, the problem is once we start going through and running multiple tests, the overall likelihood of making at least one mistake in there or at least one type 1 error starts to increase very, very quickly. And so ANOVAs can, under some situations, help with some of that, although we'll talk about some limitations down the road. But probably the greatest advantage here of our ANOVA models is it just gives us more flexibility, right? If I'm going through and wanting to put together different studies, it gives me an opportunity to incorporate more groups than just pairwise comparisons across the board, at least initially. So some greater freedom in designing and interpreting studies with our ANOVA model. Okay. So our basic structure, very, very similar to our independent sample t-test. Okay. Again, we spend a lot of time on those t-tests, but it just serves as the foundation for all these other means-based stuff. It's just kind of building on top of it. And so with our most straightforward, our one-way ANOVA model, in this situation, we've got three populations, population 1, 2, and 3, right? And what we're interested in is, do we have evidence in this study for differences in these respective populations, right? But remember, we can't sample we can't measure the populations directly because it's a hypothetical. So the mean of these three populations is some hypothetical number. I guess technically, in theory, it's out there, some specific number, but we can't test that because we don't have access to the entire population. So what we do is we sample from population 1, we sample from population 2, we sample from population 3, and based on the data that we collect from those samples, assuming they're random and representative and all of that, what we do is we start to get estimates for what the likely value of whatever we're measuring is across each one of these populations. Okay. And so, Ari, are we ever going to get a situation where we see the exact same number across our three samples?
It's probably highly unlikely.
Yeah, I think that's a fair characterization. Highly unlikely, right? And so we're almost always going to see, particularly if we have pretty good fine sensitive measurements, we're probably going to see at least some differences across our population or across our samples. And two possibilities for these differences that we're seeing. One, the differences that we're seeing across our sampling is just due to random fluctuation, right? Population 1, 2, and 3 all have identical means, right? The differences that we're seeing in the samples is just due to sampling error, right? It's just sort of random stuff, right? Or maybe the difference that we're seeing across our relative samples are the result of different population means. Population 1 has a different mean than population 2, has a different mean than population 3, and as a consequence, we're seeing that manifest in these samples, and so that the differences that we're seeing across these samples are reflective of true differences in our respective populations, okay? Which is generally what we're hoping for when we're running these types of models, okay? So again, the overall idea, the conceptual basis of this, identical to our independent sample t-test, we're just adding in adding in additional groups. Questions on this? Okay. So some terminology for ANOVA that we'll want to make sure that we're speaking the same language. If I'm talking about a factor, okay, a factor in ANOVA is some categorical IV that indicates my group, okay? So I could have experimental condition as a factor, right? Erica, let's say you're running an experimental study. You've got 4 different conditions. Condition is your factor, right? And you've got 4 levels to your condition. Allie, let's say that you're running a different, and this isn't an experimental study, but you're looking at, say, differences in hours spent studying across freshmen, sophomores, juniors, and seniors, right? Grade then is going to be your factor. Again, 4 levels to this. Ethnicity. I have an ethnicity factor. Maybe I'm looking at cultural differences across different groups of individuals, right? So ethnicity is my factor. My levels of my factor are however many sort of groups I've included in that design. Okay, so again, factor is the overall variable level. This is the individual conditions within that factor. Okay, so condition 1, 2, 3, freshman, sophomore, junior, senior, black, white, Hispanic, Asian. So these are the individual levels. The reason we're going through this is sometimes people get confused, like, well, what's my independent variable here? Well, my independent variable is sophomores. Like, well, nope, that's not your independent variable. That's one level of your independent variable. Your independent variable is class, right? Freshman, sophomore, junior, senior are individual groups within that. Okay, this starts to become important as we will get into, or what we would get into in next semester, thinking about your factor as an IV, your outcome as a DV, and thinking about this in terms of relation, right? I could ask, what are the differences in study time across study hours across freshmen, sophomore, juniors, and seniors? That's one way to ask that question. I could also say, what's the relation between class standing and hours studied, right? Just a more efficient way to kind of put that together. Basically saying the same thing. We're just talking about it as an association as opposed to mean level differences there. Okay. And so what we're going to start out today with is our one-way ANOVA model. Okay, this is our approach for looking at some differences, or looking at the relation of some individual factor with a continuous dependent variable, right? We're asking here if we're seeing evidence for differences in outcome across differing levels of whatever our independent variable is here. Okay, so again, thinking about your ANOVA, this one-way ANOVA model, it's kind of like an independent sample t-test. We just have more than two groups. Okay. All right, so this is fine, but why not just use a bunch of t-tests, right? I mean, we know what t-tests are. We're comfortable. We're familiar with independent sample t. Everybody here comfortable with independent sample t-tests? Thumbs up. Everybody loves them. We're good. We're all relative experts in independent sample t-tests. All right. So why not just do this? Why to make things complicated? Why not just go with what we know, right? Well, the main problem, the historical problem with using a bunch of independent sample t-tests, at least from a theory-based standpoint, is an inflation of my type 1 error. Okay. Remember that for any individual test, we go through and set our risk for type 1 error by setting our alpha level. Okay, and generally that's 0.05, right? But if I'm looking at Erica's study, and Erica's got 3 conditions, and Erica wants to see if we have differences across these 3 conditions, if Erica were to do this with a single or an independent sample t-test, she's got multiple opportunities for error, right? So Erica goes through and sets her alpha levels at 0.05, but we've got a 0.05 opportunity to make a type 1 error in 1 versus 2. Another 5% opportunity to make an error in 2 versus 3, and then another 5% opportunity to make an error in group 1 versus 3. Okay, with those 3 tests, we've got all combinations, but with each one of those tests carries a 5% error of claiming an effect when there isn't, in fact, an effect there to detect. And so what we see is that risk of type 1 error, the total risk of type 1 error, starts to accumulate with every test that we run. Okay, and so across these 3 comparisons, our overall chance, or our overall risk of a type 1 error, starts to approach the number of comparisons that we've made multiplied by our alpha level here. Okay, so again, across these 3 independent tests, if we're testing each one of these at alpha 0.05, my overall likelihood of it making at least one type 1 error in this set of tests is no longer 0.05. It starts to approach 0.15. Okay, so there's a 15% likelihood of me making an error in at least one of these, as opposed to each one individual ones I'm running at a 0.05 level, right? We talk about this as compounding error, as alpha inflation, and the problem is if I run enough tests, Robert, what's likely to happen?
Can you repeat the question? I cut out on there.
Yeah, yeah. So if I run enough tests with this compounding error, if I run enough tests, what's eventually going to happen?
You're not going to be able to, or the significance level is just going to get too high.
Yeah, right. I'm probably somewhere in that mix going to make a type 1 error. But do I know which test the type 1 error occurred on? No, I don't know, right? All I know is across this set of tests, it starts to become increasingly likely that one of those just popped up just due to chance, right? And so this is where we start to become concerned. And again, tends to be something that tends to be a bigger focus in experimental areas than it does sometimes with our clinical research. But if I run 50 different pairwise tests, and let's say 48 of them come up null, and I find what I'm interpreting as evidence in 2 of them, if I'm reviewing that, I'm actually not super impressed because you ran 50 different tests. Like, of course, some of them are going to pop up just due to chance, right? And so what we're concerned about with just running pairwise tests is that eventually, the more and more and more of these we run, the more and more likely something's going to pop up just as a type 1 error. Again, claiming evidence for an effect when effect isn't actually there to be found. People see what the concern is with running these multiple tests? Okay. So, what we get with our ANOVA model, at least with our omnibus test, is an examination of differences simultaneously. What I'm going to do is I'm going to look at whether or not I have differences somewhere across these 3 groups, and I'm going to keep my alpha level at 0.05. I'm going to keep my type 1 error at 0.05 and use this to see across these groups, do I have evidence of a likely difference in their respective populations? Okay. Now, this is just for 3 groups, but let's say I run an ANOVA model with 4, right? How many pairwise tests would I have to get with that? Well, I've got 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, 3 versus 4. I've got now 6 tests. If I've got 4 groups, I've got 6 tests to run. If I've got 5 groups, it just increases up and up and up, right? And so what we get with our ANOVA is a nice, or can be a nice overall test of, do we see differences? Do we have evidence of differences across these this full complement of means? Okay. Now, this inflation of type 1 error, it continues to be an issue. Again, there's no free lunch. We run into some problems with this, but we'll catch up with that down the road. All right. So people kind of on board with sort of why we've developed this ANOVA approach and how it can help us start to manage, at least initially, some of this type 1 error stuff. Okay. All right. So our hypotheses for our one-way ANOVA. Okay, our null is that population mean 1 equals population mean 2 equals population mean 3, right? If we're going to say this in words, we're going to say the means of the populations from which each sample were drawn are equal. I'm assuming that each one of my groups is coming from a distribution with an identical mean, and so my null I can state fairly easily in statistical notation: mean 1 equals mean 2 equals mean 3 equals mean 4, so on and so forth, right? Or I can say there's no effect of x on y. There's no effect of my factor on my outcome. Okay. But when we get into these multiple mean comparisons, our alternative hypothesis starts to become more difficult. I can't actually provide a statement of my alternative hypotheses in statistical notation. Why can't I just take this? Let's say we've got running a one-way ANOVA with 3 different groups. Why can't I just write mean 1 doesn't equal mean 2 doesn't equal mean 3? What's wrong with that? What do you think, Allie?
Because like maybe mean 1 equals mean 3, or I don't know, like you don't know which means don't equal which ones.
Yep, exactly, right? Mean 1 doesn't equal mean 2 doesn't equal mean 3. That's one possibility of an alternate hypothesis where this could not be true, where my null is not true. but it's one of a couple of different ones, right? Well, maybe 1 and 2 are equal, but 1 and 2 aren't equal to 3, or 1 is not equal to 2, but 2 is equal to 3, right? There are a bunch of different combinations here, right? And so if we're making a statement of our alternative hypotheses, we say at least one population mean differs from the rest, okay? Another way we can say this, we can say these data are unlikely, assuming equal population means, which gets at kind of the heart and the soul of our inferential tests, right? Basically, we're saying these are the data that we've got. These data are generally inconsistent with the assumption that all these samples were drawn from populations with equal means. Okay, so we don't have a specific alternative hypothesis in ANOVA. It's just, at least in our omnibus test that we first run, the assumption is, or the alternative hypothesis, at least one of these means differs from the rest of them. All right, and what we do is we test this in an omnibus test. Omnibus test is an overall test of significance, okay? If my omnibus test for ANOVA pops up, it says that my data are suggesting that the possibility that at least one of these populations from which our samples are drawn are differing from at least some other one, but doesn't give us any information on how they differ. It just says that there's a difference in there somewhere. Okay, so if I come up with and I reject the null with my one-way ANOVA, it says across groups 1, 2, 3, whatever, the data that I've got from there suggests that there's a population difference somewhere in there, but it doesn't tell me where it's at. It just says that there's a difference somewhere. Okay, and so we'll talk about sort of benefits of this and potential drawbacks once we sort of get a handle on this omnibus test stuff. So the test statistic that we use for our ANOVA models is going to be an F test. Okay. Now, if we think about conceptually about what our T statistic is giving us, right? Remember, our test statistic is going to be our observed differences between two groups over our expected difference if the null is true. Rachel, what's our expected difference when the null is true? What do we call that?
0? I'm sorry, I don't know.
Yeah. So, what goes in the denominator of my test statistic or my T statistic?
Standard error.
Yeah. Okay. And the standard error is just how much difference I would expect, assuming that the null is true, right? Because even if the null is true, I don't expect all my means to be identical, right? Just with my sampling distribution, I'm expecting things to jump around a little bit, right? And so our T-test is a ratio, and again, I would encourage you strongly to attend to these ratios. It helps you understand conceptually what's happening, right? In the numerator, my test statistic for my T is the difference that I've observed in my data. In the denominator, it's the difference that I would expect, assuming that the populations or the samples are drawn from populations with equal means. And if I start to get a much larger difference in my observed data than what I would expect due to just sampling differences, what am I likely to do, Erica, in that situation? Yeah. So if my T-test in the numerator is the differences that I'm observing in my sample, and in the denominator is the differences that I would expect, assuming that the populations have equal means, and I start to see a lot more difference in my observed data relative to what I would expect just due to random error, what decision am I likely to make for that test? Oh, whoops, you're on mute.
Reject that?
Yeah, reject, right? What I'm saying is these data, the differences that I'm seeing in these data exceed what I would expect just due to random sampling error. And as a consequence of that, I'm become increasingly likely to reject the null, right? And to claim evidence for an effect, okay? F-test, the test statistic we get for our ANOVA model, very similar, okay? Here what we're looking at in the numerator is the variance between across sample means over the top of variance we would expect if the null hypotheses were true or if there's no effect here, Okay, and so what we do when we get into our multiple group mean analyses, right? If we've got more than two groups, if I've got just two groups, looking at the difference between group A and group B is pretty easy, right? I just say, okay, here's this and here's that, right? But if I start to get 3 means, 4 means, 5 means, how do I come up with a number that tells me whether or not I have differences going on here, right? I can't just look at mean differences if I have more than 2 means. I need one number to tell me to identify and capture some of this difference. And so what we see and what we use with our F statistic, with our ANOVA, is we see this F statistic based on variance as opposed to mean differences. Okay, and what we can do in ANOVA speak, if you hear variance in ANOVA speak, variance just means differences. Okay, and what we're going to use in this ANOVA model is we're going to look at the variability of mean scores to start to identify and measure magnitude of differences we're seeing in this group of means. Okay, so again, just a raw difference score is easy peasy. It's awesome if we just have 2 conditions or 2 groups. As soon as we get 3 or more, now all of a sudden I can't use difference, because difference between what, right? I've got a lot of different differences I could talk about. What we do is we switch over to variance, and variance is used and variability is used. It's a synonym for differences if we're talking about these ANOVA models. So if we're looking at this, okay, I've got set 1 and set 2 here, okay, and what I'm seeing is in one set larger differences across the means as opposed to the other set. So Brittany, where am I seeing more differences across these mean scores?
Just like between the 3, the first one, the 20
okay.
and 28.
How did you know that?
Because 28 minus 20 is 8, and then 30 and 30 is the same, and then there's a 4 number difference between the
whoops, okay. Whoops, see what you did there? But what we're doing, set 1, this is one set of means. Here's 2, here's 2 set of means. So are we seeing greater differences in set 1 or set 2?
Oh, sorry.
Yeah.
Well, set 1.
Set 1. How did you know that?
Yeah. Because 35 and 20, and then 31 and 28.
Okay, right. So what I can do with this set is I can go through and I can eyeball it. So okay, we got a 10-point difference here, a 5-point difference here, 15-point difference here. Relative to set 2, I've got a 2-point difference, a 1-point difference. Here's a 3-point difference. I'm seeing more differences in set 1 as opposed to set 2, right? So I can go through and just eyeball this with a small simplified set like this, right? But if I want to calculate this and make this formula, I need to have some value that I can point to as evidence for more differences in set 1 and set 2. And this is where we could go through and we start to pull our variance, right? Riley, can you tell me what variance is?
Differences?
Yeah, exactly. How about this? Sort of remember that our variance is the sum of the squared deviations, right? Is the sum of the squared deviations divided by n minus 1, right? Divided by our degrees of freedom, right? So variance. So if we're looking at a set of scores, right, like a distribution of scores, right? And if I say, Riley, who would I expect greater variance in weight? A sample of 105-year-olds or a sample of 130-year-olds?
130-year-olds.
Yeah, why?
There would just be more difference between them. Like 5-year-olds all pretty much weigh the same.
Okay. Right. So again, we're taking this idea of, in my sample of 5-year-olds, if I'm sort of looking at the weight of 5-year-olds, not that they're all going to be the same, but they're probably going to be closer together around that mean than 100 weight of 130-year-olds, right? So more variability. This same idea, what we're doing is we're utilizing and recognizing variability and variance as a measure of differences across a set of scores, and weaponizing that in ANOVA and using variance as a measure of differences, right? So, Brittany, you can eyeball set 1 and set 2 and say, yeah, there's more different. These are more different than this, right? But if I want to do this formally, what I can do is I can go down through and take a look at the variance, right? Here, the variance of set 1 is 58.3. Set 2, the variance is 2.3. This is a bigger number than that, right? So I'm saying there's more variability in this set of scores than in the second set of scores, okay? So in ANOVA, if I'm seeing large mean differences, I'm going to get a larger variance estimate. If I'm seeing less mean differences, I'm going to end up with a smaller variance estimate. Do people see how we're using variance as an indicator of differences across a set of scores here? Kind of clicking. Okay. All right. And so what we want to do with our ANOVA models is we want to partial the variability in our sample data, right? Or the differences in our sample data, determine the presence of differences across different groups. And we do this in a couple different ways. What we're going to do is we're going to take our total data, and with our ANOVA model, we're going to separate this into what we're going to call between treatment variance and within treatment variance. And again, we use treatment just because that's ANOVA talk for differences. It's just kind of classically how this is developed. But what we're going to do is we're going to take all the variability we're seeing in our data, and we're going to section this off into stuff that's happening across groups and stuff that's happening within groups. Okay. So if we start with our between group differences, and in your handouts, you're going to have that your ANOVA handout, your ANOVA worksheet. That's just pulling things off here. Okay, and so what we've got is a hypothetical study here where what we're doing is we're interested in the impact of heat or temperature, room temperature on performance, right? The idea being that, if I'm taking an exam and things are too chilly, that might impact my performance. And if things are too hot, it might impact my performance. We got a Goldilocks situation in here where maybe there's sort of an optimal level of room temperature for performance on something, okay? And so here we've got a very small study. We've got 3 different groups or 3 different conditions, right? So this is our factor. Temperature is our factor. We've got 3 levels to our factor. And within each level of our factor, within each group, we've got 5 different scores, okay? And if we go down here, we're looking to see the mean of group 1, mean of group 2, and the mean of group 3, right? What we're seeing in terms of a couple different options and things that drive these differences that we're seeing here is going to be systematic differences caused by actual differences in the respective population. So, and this is my effect. So one possible reason I'm seeing differences down here in my mean values is going to be because there are actually population level differences in performance in the hypothetical population completing this evaluation in 50 degrees, at 7 degrees, and 90 degrees. Like the actual performance in our hypothetical populations is different, and those differences that we see at the population level are driving the differences that we're seeing across our within our sample. Okay. Other option or other possibility is that we're seeing differences across sort of these things due to a couple different sources of error. One are going to be random non-systematic differences. Okay, what I'm saying is maybe that the differences in my 3 means here are due to systematic effects, but maybe not. Maybe there's just experimental error, just random stuff going on, just random differences in the people who we have in each one of our groups. And so there's some level of random differences that we're seeing that are just causing variation. Okay, so maybe these differences that we're seeing across these 3 groups aren't due to anything systematic going on in performance across the respective populations. Maybe it's just random stuff. Okay, or maybe there are systematic differences unrelated to my grouping factor. Okay, maybe there are confounds. Maybe something about this increased score, testing scores in this group isn't due to temperature. Maybe it's due to something else that I haven't measured. But if I haven't measured it, and we're seeing differences due to something that I haven't measured, what do we call that? At least from this perspective of my model. If it's something that my model hasn't accounted for, how might we qualify that?
It's the confound, right?
Yeah, and what would we call what would we call it? Yeah, if I'm seeing differences due to a confound that aren't accounted for my model, what do I call that, Brittany?
I'm trying to pull it out of my. I don't want to say third variable, but
No, the third variable could be a thing that contributes to it, but from the purpose of my model, I'm seeing differences due to something that's not accounted for my model, and if it's not accounted for my model, it's going to be error.
oh,
Right? Okay. So what we're going to see down here is we're going to see differences in these across my means that could be due to actual systematic effects, or it could be due to error, right? And error can be random error, just kind of random fluctuations, or it can be systematic stuff that we haven't accounted for in my model, right? Or maybe in my study, I have RA1 running this group and RA2 running this group and RA3 running this group. And maybe RA3 is just doing something different. It's not random. They're scoring stuff wrong in this condition, right? It's systematic. It's not random stuff, but it's not something that we've accounted for in my model. And so as a consequence of that, it's error. Okay. Anything that's not accounted for in my model, anything in my analyses that isn't explicitly attached to some sort of measured variable is error. It all gets dumped in that error term. Okay. So again, Erica, where do we see group level differences in our table here? What's that?
Within each group.
Okay. Where am I finding group level differences?
The means.
Yeah, right here. Okay. This is my group level difference, right? What I'm looking at is I've got people completing my evaluation in condition A, condition B, condition C. The mean levels, the difference I'm seeing across those mean levels, those are my group level differences in ANOVA. Okay. Questions on our between group differences? Okay. And what we're going to do here is we're going to look at, because again, I have more than 3 data points or more than 3 means. So all of a sudden, just individual or differences, group level differences go out the window in terms of like different scores. So what I can start to do though is I can start to look at the variability of these scores. And Robert, if I say I have more variability in my scores, what does that mean?
That means there's more difference between each score.
Yeah, exactly.
Quick question.
Yeah.
So is error gonna be, especially in like psychological research, is it sort of gonna be like the idea like how the null is never false? Like, isn't there always gonna be?
Yeah.
Okay.
Yeah. We're always going to have error. Now, the assumption of our statistical models that we've measured our stuff without error, right? And that our models are appropriately specified so that everything that's needs to be in there is in there and everything that's not is not, right? But that's never going to happen, right? And so wanting to be thinking about the vulnerabilities of our model. So perfect. Okay. And Ari, if I'm thinking about an ANOVA model, do I want to see more higher levels of between group differences or lower levels of between group differences in most cases? Yeah, right. Presumably, I'm running this ANOVA model because I'm hypothesizing that these populations are different in some way that I'm looking at, right? So I'm hoping for large between group variability because that's going to tell me that my groups are sort of farther apart than if they're not, right? If I have low variability or little variability across my groups, it means that everybody's scoring right about the same. Okay. All right. Within group differences, right? If I'm running an experimental study, and I think experimental studies are the nice way to think about this, but if I'm looking at an experimental design, within each individual condition, if I'm running a tight experiment, everybody within a condition is getting the exact same thing, okay? So everybody who's in this treatment 1 is getting the same procedures. Everybody in condition 2 is getting the same procedures. Everybody in treatment 3 is getting the same procedures, okay? So as a consequence, within a given group, there's no systematic differences in my manipulation that should cause differences within my group, okay? And so as a consequence, any differences I see within a group are going to be the product of some just random fluctuations or some unmeasured influences, right? And Brittany, what do I call unmeasured influences in statistical analyses? Error, right? So that's error and standard error, right? Those are two good guesses. If you come up short on something, just say, I don't know, standard error or error. I don't know. Statistically, it's a good guess, okay? And the differences that we can see within groups, right, are going to be just individual differences, just because people are different. So people are all going to be a little bit different, or it could be due to some sort of experimental error. I'm not running a tight study, right? My RAs aren't trained super well. And so depending on who you get or who you work with, there's different stuff going different things. And so we start to see experimental error going on within this, okay? Rachel, where do we see within group differences?
Within the scores?
Yeah, what do you mean within the scores?
Like within the scores of one group or?
Yeah, right. So within here. So, Natalie, if I'm looking at this, if on whatever task I'm having people do, if temperature is the only thing that determines your performance on this task, what should all the scores within a condition look like? Yeah. Similar or the same?
Well, the same.
Yeah. So if I'm running a study, right, or if I have a task where temperature is the only thing in the universe that determines performance on that task, then I should see everybody in a condition to have not similar, exactly the same scores, right? But that's never going to happen. One, because we work in psychology and there's never one determining factor. There's always lots of stuff, right? And our measures are really fuzzy, and we've got tons of individual differences, right? So we're always going to see some level of differences within group variability, within group differences, right? But what we're hoping for is if we've got good experiments, good measures, and we've accounted for most of the things going on, that the stuff that we're seeing within groups or within a condition, that the variability in scores within a condition is going to be relatively small. Okay. So, yeah, within an ANOVA model, what do we call within group variability? Brittany?
Within group variability?
Yeah, what do we call that?
Variance?
Well, we would call it.
Not error.
Yeah, it is error. Congratulations. Yeah. See, I'm setting you up to crush these and knock these out of the park. Yeah, it's error, right? Because if I'm running a one ANOVA, I'm looking at differences across this, and this. And so if I'm seeing differences within group, it's error. It's something that's not accounted for my model, and anything not accounted for my model is error. Okay. All right. So when I'm looking at my F ratio, right? My test statistic, F ratio is my test statistic for ANOVA, and what I'm going to do is I'm going to partial out two different types of variability here. I got my between treatment variance. Rachel, what do I call my between treatment variance? What does that represent?
questions? Because I don't know.
Yeah. So I'm looking at my between treatment variance. My difference is what? Go for it.
Differences in means?
Yeah, and what does that represent? Potentially represent, at least. Am I hoping for differences?
Between in effect?
Yeah, yeah. So my between treatment variance, this is my effect, right? These are the differences that I'm hoping come up, and the variability across my means that I'm hoping to come up, just due to the fact that I'm hypothesizing that these respective populations are different on something. So up here in the numerator, my between treatment variance, this is my effect, okay? And then we're taking my within treatment or between treatment effect over with my within treatment effect. Brittany, what do I call my within treatment variance? Error. Okay. And so conceptually, we've got over the top, remembering that variance is ANOVA code for differences. I've got my observed group differences over the differences that I would expect just given the null, right? If, going back to my thing, if treatment 1, or if group 1, group 2, group 3, if these respective populations all have equal means, right? No differences. I would expect then for the amount of differences that I'm seeing across group to be about the same as what I'm seeing within group, right? Suggesting a lack of effects here. So what we've got is that we've got our observed group differences over our differences expected under the null, just like our t-test, right? We can also think about this as our between treatment variance. This is due to systematic effects plus random differences over the top of random differences, right? And so this ends up giving us two different scenarios, right? If I have no systematic effects of group, right? If population 1, 2, and 3 all have identical means, right? What I would expect then is no systematic group differences, and the differences that I'm seeing across my treatments is entirely due to sort of error or some other effects, right? So in this situation, I've got no group effects plus random differences over random differences. I'm going to end up with an F value that's very close to 1. Okay. Alternatively, what I've got is I've got differences across my groups that are due to some systematic difference in my population. My groups are different because the populations which I'm drawing these samples from are different in some way that I'm interested in. And so what we have here then is a systematic effect plus my random differences over my random differences. I cross this out and I'm going to get some value that's systematically greater than 1 here. So conceptually, are people seeing kind of what this statistic is tapping into, where we're going with this stuff? Questions on this? Okay. So what we're doing with our ANOVA model is what we're going to do is we're going to take the total variability in our data set. Okay, so this is our full set. This is all the stuff that's going on. And what we're going to do is we're just going to section this up. We're going to partition in our ANOVA model into two different types of variance. We're going to have between treatment variance and within treatment variance. Between treatment variance, this is going to be due to our actual population level differences and some chance variation. My within treatment variance, this is going to be the differences in scores we see within a group, and this is going to be just due to sort of random error and chance and sort of anything that's not in our model, and just also random things. Okay, and so what we're hoping, just like our t-test, right? What we're hoping is that the variability that we see across groups is going to exceed the variability that we would expect just due to random differences, allowing us to go through and claim support for our hypotheses. Okay. So again, remember that our sum of squares, and we're going to get into this because a lot of ANOVA gets into sum of squares. Sum of squares, variance, standard deviation, these are all just measures of variability. Okay, they're just different metrics. And if I'm talking about, when I'm going through and talking, if I'm talking about variance, I'm talking about a specific statistic. Sample variance is going to be our sum of squares over our degrees of freedom, right? Variability, this is just any measure of variability, right? So again, when I'm working within ANOVA, variability means differences, right? We can't just look at mean differences because I've got too many means. So different mean differences start to become less useful. But what I can do is I can start looking at the variance of different scores. And if I've got more variance or more variability, it means these scores are much more different than if I have low variability. It means it's less different. So again, as I'm walking through here, if I'm talking about variability in general, it's just talking about differences. Variance, sums of squares, standard deviations, these are just specific metrics of variability. Questions on any of this? Okay, cool. Let's go through, let's take a 10-minute break, come back at 3:16, and we will jump into sort of how we go through and partition these data up. Okay, awesome. Cool. All right. Anybody have questions about? Yes.
This isn't about that. Did you just say a $200 impulse buy?
Yeah.
No?
Well, we needed it. I don't know. I sort of purchased it, and then came home and went right in to talk to you guys before. Divulged to Tara. She sent me to get potting soil and a plant potter, and I came back with that and also a tool. So, because we need to get that shelf attached to the wall, because otherwise it come down harm. Don't want anybody to be endangered. Right? Someday COVID will be over. And I don't know, maybe we invite you guys over and Robert's climbing on the bookshelf and it tops over on him, right? That's a mess. That's a lawsuit waiting to happen right there. So, well worth the money spent on the front end to avoid multi-million-dollar lawsuit by Robert, because he was climbing on the bookshelf after I told him several times not to crawl on the bookshelf. He did it anyway, but still, that's why you have a homeowner's insurance. That wasn't mine. That was Tara's. That was, yeah, right? See, it's for the safety and comfort. That one, too, so Robert didn't freeze to death. That would have been another whole sort of situation on my hands, right? So, all right, cool. How are we feeling about ANOVA stuff up to this point? Feeling all right? Or is it like, maybe, right? All right. The thing to remember here is getting into your head this idea of variability, right? Variability just is talking about differences, right? And sort of partitioning this into differences that we're seeing across groups, which is generally what we want to see, right? I want to see differences in my mean scores across groups. That's a good thing. Variability within groups, that's less good, right? If I've got a tight experiment and sort of whatever I'm measuring is the thing that's determining performance on whatever my outcome is, I'm wanting to see pretty much everybody across different experimental conditions or different groups to be kind of in the same area, right? And so what we want to see is we want to see more variability across groups than we're seeing within groups, because that suggests an effect and sort of becoming more likely that we can claim evidence for whatever it is that we're looking at. Okay, so going back to our components. All right, so this is something that we're going to spend some time here walking through, like the hand calculations of ANOVA. Now, will you, over the course of your career, ever need to hand calculate an ANOVA? I'm not going to say never, but it's probably unlikely, okay? But what we want to do, I think stepping through this, hopefully will give you an idea for where these numbers are coming from. Like, the worst thing you can do in any type of analysis is just have no clue about where anything's coming from, and it's all a mystery, and you have to take it on faith. It's hard to diagnose things and sort of problem solve. And so as we're working through here, wanting to show you where these numbers are coming from in these ANOVA table, and then this is also going to set a stage and be helpful for later regression models, just general work with sums of squares and things like that. Okay, so when we're going through and we're calculating our ANOVA, we've got an ANOVA being a combination of a number of different interrelated figures. Organizing this by table starts to become helpful because we can start to go through and double check, make sure everything is squaring up the way it should with our analyses. So we're going to have variability or variance that we're capturing that we're associated with treatment, and this is just our between groups variability. We've got our error. This is our within groups variability, and this is our total variability. We're just going to go through and use these figures to go through and calculate our F statistic here. So for this sequence of slides, just some notation. One of the most difficult pieces of going through and reading through methods literature is getting square on the notation, because it will change sometimes. For the purposes of our example here, K is going to be equal to the number of the levels of our factor, okay, the number of groups that we have or conditions we have within our factor. Lowercase n, this is our number of scores within condition. Uppercase n, this is the total number of scores in our entire study. Capital T, this is the sum of all scores within each condition. So this is our treatment total, okay? And then G, the sum of all scores for the entire study. This is our grand total, okay? And so again, have this, as we're working through, have this sheet up so you can go back through and correspond to some of the figures that we'll have up on here. All right. So with this handout, here are sum of x, right? This figure right here. This is just the sum of all our squared scores for everybody in the sample. So if I take 0 squared plus 1 squared plus 3 squared was 1 squared plus 0 squared plus 4 squared, so on and so forth, this is going to get us to 106. Okay. G, this is the sum of all scores. So if I add up all my scores, I'm going to get 30. Okay. N is the total number of scores, got 15 observations in this analysis. K, the number of level of groups. So I've got 3 groups here, group 1, 2, 3, with each one of these conditions. Down here, again, T is going to be my total of my scores within each group. This is my sum of squared. This is my sum of squared deviations for each group. And remember, the sum of my squared deviations is just my score, the square of my score, or excuse me, my score minus my mean value squared, right? And the sum of the squared deviations is the sum of my squared deviation scores. So lowercase n, total number of scores at each group, and m is going to be the mean of each group. Okay, so down here is we're seeing this is my between groups variability, or my between group variance. Here, within group variance, and these are the different figures that we'll use to calculate our ANOVA table. So again, here we're seeing variability both between and within conditions. We've got variability across conditions 1, 4, 1, right, telling us that these are different. Within groups, we're seeing variability here. And so what we need to do with this ANOVA analysis is start to partition this out into between and within. Okay, yeah, there's my between, there's my within. All right. So first thing that we're going to calculate. Now, as you're going through and doing this, you don't have to always step through it this way. We're going to do it because it'll make the most sense, but later you might sort of change this around. But if we're going to go through and calculate our sum of scores total, sum of scores total, this is our total variability for our entire set of scores. Okay, and this is going to be calculated. We've got a couple different ways of thinking about this. This is going to be like the conceptual, like the definitional model. This is going to be computational, how we can go through and calculate it. But essentially what we're doing to get our sum of scores total, we're taking score for person I in group J and subtracting it from the grand mean and squaring that. Okay, so if I take Brittany's score and I subtract it from the grand mean and square that, and then I take Rachel's score, subtract it from the grand mean, square that, take Natalie's score, subtract it from the grand mean, square that, go through that and do that for everybody in the sample. This is going to give me my sum of squares total. Okay, and so again, this is going to reflect the sum of the squared deviations of person I in group J from our grand mean. Okay? Think about this as all the variability in my sample. Okay, this is my total variability split to a combination of between and within group variability. This sum of squares total is going to be equal to, if I just took everybody in my sample and calculated the variability or the variance of everybody in my sample, this is going to be my sum of squares total, right? So like in your screening, you know how you're going, like, go through and like, oh, I'm looking at the standard deviation of everybody in my sample and calculate the variance. That's just what your sum of squares total is. It's just all the variability in your scores. Okay. The degrees of freedom for my sum of squares total is just going to be one less than the total number of scores. So it's just going to be n minus 1. Easy peasy. Okay. So this is the conceptual sort of formula for sum of squares total, but it's easier. So these two are mathematically equivalent. What we can do, this has no real ties to conceptually what's going on, but we can get the same number if we take the sum of our squared scores and subtract the square of our grand total divided by n, right? So if we do this, again, if you're looking on your sheet, the sum of all my squared x's is 106 minus my square of my take the square of my grand total divided by the total number of scores I have in my set. Degrees of freedom here, 15 minus 1, going to give me a sum of squares total of 46, degrees of freedom 14. People comfortable with this, what we did here? Following along? Okay, cool. Next thing we're going to calculate is my sum of squares error. Okay, sum of squares error is the variability that we're seeing within each treatment or group. Okay, again, thinking about if whatever I'm measuring, whatever my factor is, if that's the only thing that's determining scores, everybody within a group should have identical scores, right? But they're not. There's going to be differences. People are going to differ for reasons that we don't know or haven't measured, and because of that, we're going to call this error, right? So our sum of squares error, we're calculating variability or variance within each group. What we're going to do here is we're going to calculate this as the sum of the squared deviations of person I in group J from their respective group mean. Okay, for total, we were calculating deviation from the grand mean. Here, we're looking at how far is Brittany, Rachel, Ari, and Robert from their group mean, right? How much variability are we seeing? How much are people differing from where their group's at? Okay. We can also calculate sum of squares error as the sum of squares within each group, right? It's pretty straightforward stuff here. And again, thinking about your sum of squares error as a variability within groups due to individual differences, experimental error, anything that we haven't measured or captured in this study can contribute to this within group error. Okay, this sum of squares error, you see this referred to as your error term. This is going to start to become important when we get into post hoc tests and follow-up tests and things along these lines. Okay, so again, we're assuming that any differences that we're seeing within a group is due to error. Degrees of freedom for our sum of squares error is given as the total number of scores minus the number of levels in each factor, so n minus k here. So my sum of squares error, and again, so you can see we're just building in the table here, is going to be my sum of squares, the sum of my sum of squares per group. And if we go to your table here, you see sum of squares for group 1 is 6, sum of squares for group 2 is 6, sum of squares for group 3 is 4. We just add those up. Degrees of freedom, total number of people in my sample minus the number of groups, 15 minus 3, gives us a sum of squares of 16 and a degrees of freedom of 12. People following on that? Okay. And the last thing we're going to calculate is our sum of squares treatment. Okay. This is our variability or our differences across my different conditions or groups here. Okay. And if we're using, so how we're going to go through and calculate this is going to look a little bit different if you got a balanced design where we have the same number of people for each group, or an unbalanced design where we have unequal sample sizes across group. Okay. If I have a balanced design, my sum of squares treatment is just going to be the sum of the squared deviations of the group mean, of the mean of group J from the grand mean multiplied by the number of people in each cell, right? So here I've got, for a balanced design, meaning I have the same number of people across each group, I've got the mean of group 1 minus the grand mean squared, plus the mean of group 2 minus the grand mean squared, mean of group 3 minus the grand mean squared. Take that sum, multiply it by the number of people I have in each cell. That's going to give me my sum of squares treatment. Okay. With unequal sample size, it gets a little bit different. What I do is I take the squared deviation of each group from the grand mean and multiply that by the number of people in that group, in group J, and then take the mean of group 2 minus the grand mean, square that times the number of people in group 2, plus the mean of group 3 minus the grand mean, square that times the number of people in group 3, and then just add those figures up to get to my sum of squares treatment for my unbalanced design. Or I can calculate it by addition subtraction. If I take my sum of squares total and I subtract my sum of squares error, what am I left over? Everything else is with between group treatment stuff, and so I can get it that way. So again, sum of squares treatment is the variability that's remaining in my data after I pull out within group error. This sum of squares treatment is going to take my effects of interest plus any sort of additional random error that's caused differences across my groups. Okay. And again, my degrees of freedom for my sum of squares treatment, one less than the number of levels to my factor. So here we've got k minus 1. So here we've calculated our sum of squares total, sum of squares error. Now we calculate our sum of squares treatment. We can do this quick and easy by subtraction, right? If I take 46 minus 16, what's left over is 30. Degrees of freedom, I got 3 levels, minus 1 is 2. Going to go through and plug that in. Okay. Questions? Feeling okay with this? All right. So, got these first two columns filled in. But what we want to do now, and again, we're going to talk about things. We have to speak ANOVA here. Is we're going to calculate our mean squared. Mean square is just ANOVA term for variance. If you hear mean square, it just means actual variance, right? Just like variance that we've been working with and counting up to this point all semester. Okay. So remember that when we're talking about our F ratio, it's the ratio between treatment variance to within treatment variance. And so again, for whatever reason, I'm not sure why, ANOVA just calls this mean square. Mean square is just a variance estimate, okay? And so remember that because mean squared is just a variance estimate, all we need to do is use our original variance formula to go through and calculate our mean squared treatment and mean squared error, right? Remember that remember that variance is just a sum of squares estimate divided by the degrees of freedom. That gives me variance. So for my mean squared for my treatment, this is just my variance between groups. My sum of squares treatment over degrees of freedom treatment. Mean squared error, this is my variance within groups. Sum of squares error divided by sum of degrees of freedom error. Our mean squared error here is just the pooled variance of across all of my cells. Okay, remember this. This is going to start to become important when we get into our follow-up tests and our post hoc stuff. Your mean squared error from your ANOVA model is just your pooled variance estimate across all three conditions. So this is easy. Mean squared treatment is just my sum of squares divided by my degrees of freedom. Error variance is just my sum of squares divided by my degrees of freedom. You get 15, 1.33 here. And again, this is just variance. Mean squared, just variance. Your error term is just a pooled variance within your pooled variance across your across your treatments. Okay, so all of this building up to the calculation of our F ratio. Okay, F ratio, this is our statistic for ANOVA, and again, this is just the mean squared treatment over the mean squared error, or the variance, or my between treatment variance and over my pooled within treatment variance, right? So again, thinking of this conceptually as my observed group level differences over the differences I would expect just due to randomness and error, which is going to be, I'm estimating as sort of the variability that I'm seeing within groups. Okay? So again, if I'm thinking about it this way, if sample A, sample B, and sample C were all pulled from populations with equal means, what I would expect is the variability that I saw within groups to be about the same as the variability I see with across groups. And if that's the case, I'm going to get an F ratio that's very close to 1, and I'm probably going to fail to reject. But if I'm saying group level differences that are larger in magnitude than the stuff that I'm seeing within groups, that's suggesting some evidence of some systematic differences across these populations that's manifesting in my samples. I'll go through and calculate that and start to get an F ratio that gets larger and larger that will provide me evidence of an actual effect. So here, my F ratio is just going to be my mean squared treatment over my mean squared error, going to give me an F value of 11.28 here. All right. People see how we went through, calculated all this stuff? Now, the nice thing about my ANOVA table is this, it's got built-in checks, right? I can go through, if I take my sum of scores treatment and add my sum of scores error, I should get my sum of scores total. Same thing if I take my degrees of freedom treatment, degrees of freedom error, should give me my degrees of freedom total. My mean squared error should be my sum of scores treatment divided by degrees of freedom. Mean squared error, sum of scores error divided by degrees of freedom. This divided by this gives me my F ratio. Everything fits together. Everything squares to 1 here in order to go through and check. So if I'm doing this, I can go through and say, if something doesn't fit here, I've made an error in my calculation, something's off. All right. So I guess any questions about the calculation of our ANOVA table in this one-way design? All right, cool. So, again, sort of thinking from a conceptual standpoint of our one-way ANOVA, what we've got here is we ultimately arrive at an omnibus F. This is just going to be my variance between treatments over my variance within treatments. Again, my between, just my sum of scores between divided by degrees of freedom between, sum of scores within, degrees of freedom between. And what we're doing here is we're just partitioning all the variance that we have in our data. All the variance that we're seeing, all the variability in our data, we're just sectionating it out and saying, all right, this is what we're seeing between groups, this is what we're seeing within groups, going through and comparing those in order to try and get a signal for evidence that our individual samples were drawn from populations having different means. Conceptually, how are people feeling with this? Starting to see how this kind of fits or works through? Okay. All right. So thinking about a different way to think about this. So what we've just gone through is the classic example of ANOVA. We can also think about this from a general linear modeling approach. Okay, this is something that's going to be more useful as we start to get into other areas, right? But if we're thinking about this, let's say we're interested in mean differences in weight in sort of North America, right? And so we say we've got a population mean in the United States, let's say of 185 pounds. Average mean for men is 200 pounds. Women, it's 170. That seems high, but whatever. Let's sort of call it that. Okay. What we have in terms of my grand mean, this is my best guess. So if I were to randomly select anybody from the U.S., if these are real parameters, right? If I were to select any random person from the U.S., any adult, and I didn't see them, and I had no information about that individual, Riley, what's my best guess on the weight of this person in the absence of any other information?
But they would weigh 200 pounds if they were a man and 170 if they were a woman.
All right, but I don't know that. I don't know anything. I just tell you, hey Riley, I here have individual X. How much do they weigh? What's your best guess? Based on this table up here.
185.
185, right? And so what we can think about in this case, in ANOVA, is your grand mean just being your best guess for anybody's individual score without knowing anything else about them. I don't know what condition they come from, right? I'm just going to guess the grand mean. This is my best guess outside of any additional information, right? What I can think about then is adding in a group model, okay? With my group model, what I've got is, now you tell me in this situation whether or not I'm talking about a man or whether or not I'm talking about a woman, right? And this is my group model. And so what I'm going to do here is I'm going to take my grand mean, and I'm going to add whatever the deviation is from this group from the grand mean, okay? So if you say person X is a woman, I'm going to take 170, and I'm going to subtract 85 and add that to my grand mean. Or if you say it's a man, I'm going to take 200 minus my grand mean and add that to my mean, okay? So what you can think about here is I'm starting out with my grand mean. And then what I'm going to do is I'm going to make an adjustment based on you telling me which group they come through, right? If I take 170 minus 185, if you tell me it's a woman, this is going to be actually a negative number, and so I'm going to end up subtracting a little off my grand mean. If it's a man, I'm going to have an addition of 15 points, right? And so I'm going to add 15, right? And so what we're doing here is we're making an adjustment, right? And so what this is doing is giving us better information about than just predicting sort of the overall population or a group level mean, because I'm sort of functionally increasing or decreasing. And if I go through, this is a deviation score, right? Essentially what I'm doing here is I'm predicting the group mean, okay? So let's say, going back, Riley, so you say, okay, here's person X. What's their weight? You say, well, I'm going to guess 185. And I say, okay, well, let me tell you also that this is a man. So you're going to take 200 or 185 plus the deviation of 200 minus 185, which is going to be 15. So you're going to take 185 plus 15, which gives you what?
200.
200. So basically my group model is just predicting my group level mean. Okay. So even that, do you think that that 200 is going to be the exact weight of that person?
No.
No, right? I'm going to have fluctuation even among men, among women, right? But again, statistically, it's my best guess for that individual. Okay. And then what we get into here is a full structural model where we start to add in. So I've gone through and I've taken my grand mean. I've made an adjustment based on the group. And then here at the end, what I'm doing is I'm taking that individual's score and subtracting it from their group mean and sort of adding that onto the end. This is my error term, right? This is how much that individual deviates from their group level mean, right? So my full structural model here ends up being an additive function of my group mean, right? My specific group or my grand mean, my specific effect of my group, whether or not we're taking that weight adjustment, we're increasing it or decreasing it, whether or not you tell me it's the person that I have that's been randomly selected is male or female. And then what we've got is the error associated with that individual, their deviation from their group mean, right? And if I take the grand mean plus the group effect plus however much they've deviated from their group level mean, this is going to give me the exact score for that person. Okay. So just a different way to think about it as we start to get into, don't worry about this too much. Okay. What this is this is just as we start to get into regression models and other complex analyses, we start to think about these models as an additive function of different factors and things like that. As we go through, we make adjustments up and down based on predicted factors. And this is just an alternative way to think about this conceptually that will be helpful down the road. For right now, you don't have to worry about it too much, but just be aware when we're talking about a generalized linear model approach, this is kind of what we're talking about. Okay, questions on any of this?
So the E isn't the constant E, it's just however much the individual differences.
Yep, exactly. Erica, and so, you know, for a lot of stuff that like Ben does with some of the longitudinal modeling with stuff, this is the basis for that, right? So we're going through and we've got a number of different predictors, and not just a group level predictor, but a lot of different stuff. And so we always start with sort of the mean for everybody, and then we start making adjustments up and down, right? But eventually we're going to account for all of our predictors, and then we're going to have some error term, some residual, right? Because people are rarely going to fall exactly on their predicted value. And that E term is going to differ. You'll notice the notation. This is the error term for person I in group J. So this error term is going to be slightly different for everybody, or maybe largely different for everybody, depending on how much error that we have in our model. And that just gets tacked on to the end. Basically, my guess for any random person's weight in this analysis is going to be the group mean, or the overall mean, plus the group effect, whether or not we're shifting that up or down, plus whatever deviation that individual has relative to their respective group. It's just a nice way if you can start to think about these or recognize that this is an alternative way to think about things. Starts to become helpful when you get into some more advanced models where this is really does a better job of mapping onto stuff. All right. So if we're talking about critical values for F, okay, our F distribution, again, because we calculate F as the ratio of two variances, F is always going to be positive, right? Can I have negative variance? Is that a thing, Robert? No, you're right. I can't have less than no differences, right? So because my numerator and my denominator are always going to be positive, my ratio is always going to be positive, right? And so again, we've got a different distribution. When my null hypothesis is true, I'm going to have F values that are very close to 1, right? And so what we would expect then is under the null hypothesis, instead of having like a t value where we're going to have sometimes scores are above, sometimes below, because F can only take on positive values, we're going to have, if the null hypothesis is correct, we're going to have a value very close to 1. And so we get under the null distribution, most of our cases piling up around 1. But if there's only so far in the negative or in the sort of the direction close to 0 that it can go, we can get increasingly larger and larger and larger F values. So what we do is we get this skewed distribution here. Okay, like our T distribution, we don't have an F distribution. We have an infinite number of F distributions based on our degrees of freedom. Okay, and so what we have is a family, just like T, we have a family of curves instead of one curve that goes through, and sort of the shapes look a little bit different depending on our degrees of freedom. Okay, so if I'm looking at, for our example here, right, if I'm looking at my critical F value for 2 and 12 degrees of freedom, all right, 2 degrees of freedom, this is the degrees of freedom for my between, 12 is degrees of freedom for my error, right? So with the F distribution, I have 2 degrees of freedom instead of just 1. And so if I go through, find an F distribution with 2 and 12 degrees of freedom, at alpha 0.05, it's going to give me a value, a critical value of 3.88. Our F value here was 11.3. So that's existing, I don't know, way out here. There's a way high, right? And so what we would do then is we would reject the null hypotheses under this analysis. We want to look at, trying to find, your F table here. So again, I've got 2 degrees of freedom in the numerator, right? Because I had 3 groups, subtract 1, I got 2 degrees of freedom in the numerator, 12 degrees of freedom in my denominator. I go down here, 2 degrees of freedom, 12 degrees of freedom, you got 3.89. So there's my critical value, right? Alternatively, here's I just Googled critical F value, and it's just this Daniel Soper thing. So I've got 2 degrees of freedom in the numerator, 12 in the denominator. Calculate, right? It gives me 3.89. Same thing here, right? So this is my critical value for my F table. I can get that either way. And what this is going to do is it's sort of going to go through and be able to reject the null here. Questions on F distributions and what we've got going on here. All right. Now, something that's important, and this will be useful. It seems like won't be a useful thing, but it will be useful. Trust me, sometime in your history, you'll be like, oh, sweet, I'm glad Josh told me that. We've got a direct relation between my T and my F distribution. Okay. My F distribution with 1 and sort of whatever degrees of freedom is going to be equal to my T distribution, the square of my T distribution. All right. If I go through and pull in well, here, let me do this. Okay, so let's say I've got a critical T value of, say I got a T with 30 degrees of freedom, let's say. Okay, calculate that, and I get a T value of 2.042. All right, someone take 2.042 and square that, or yeah, square that, and tell me what they get. What did you get, Robert? 4.169. Okay. So if we go to our F, and so we said, okay, so if we go 1 degree of freedom, 30 degrees of freedom in the denominator, 4.169, right? 4.17. Okay. So it's the same thing. An F distribution, at least an F with 1 degree of freedom, is just an F with 1 degree of freedom in the numerator is just the square of a T distribution. So remember, we had talked about you can run an ANOVA with 2 groups. That's perfectly legal. It's fine. It's functionally identical to a T-test, right? So if I had Group A and Group B, I could run an ANOVA model on that. Now, I wouldn't, just because people understand T-tests better, but I could run it as an ANOVA. And there's actually more of a tradition in experimental psychology to report things sometimes two group tests, sometimes as Fs, and it's perfectly legal. All they just did is they just ran an ANOVA with just 2 groups and reported it as an F, right? And so again, if I'm running F statistics with one-way ANOVA on a factor with just 2 levels, it's functionally mathematically equivalent to an independent sample t-test. So I can take my F is equal to the square of my t is equal to the square root of F. I can move back and forth between these. It's the same statistic, okay? And where this can be helpful, and so again, yeah, if we go through and look at a t-value with a 2-tailed test, degrees of freedom 20, compare that with a critical F with 1 and 20 degrees of freedom, we can go back through and move back and forth with this, okay? And so where this starts to become helpful, remember, is that if I'm reading a paper, let's say, and they've reported a mean-based comparison, a pairwise comparison, and they've reported it as an F, and they give me their F statistic, but they haven't reported means or standard deviations for anything, I can go through and calculate an effect size based on that F statistic, because I know that F is related in the two group situation. I know that F is just t squared. So I could take F and I could take the square root of F to get an approximation of my t statistic. And I know that I can calculate a d statistic based on a t statistic. And so I can go through and translate t to d. And now all of a sudden I've got an effect size for that F test, even though Bozo author didn't give me any of the stuff that I would like to have to calculate it directly, right? So recognizing the relation between these statistics can be very, very helpful for going back through and doing some detective work and getting statistics that you want to know, right? Because maybe, Ari, you're wanting to run a power analysis for your study, but the only study that's done something similar to what you want to do is reporting a pairwise comparison as an F, but they didn't report means or standard deviations. You can still work backwards and get that number, that estimate of effect, even if they didn't report it just based on the stuff that's in there. Okay, so just recognizing that we can go back and forth with this. Okay, now if we've got more than one group or more than 2 groups, then this doesn't work. But an F statistic with 1 degree of freedom in the numerator just is telling us we're making a comparison across 2 groups. We can work backwards from that. All right. So here, my hypothesis is going to be in statistical notation. Mean performance in 50-degree temp is equal to 70-degree temp is equal to 90-degree temp. Our alternative, mean learning will differ in at least 1 temperature condition. Okay. My conclusion based on my study here, and again, this is a little bit different because we're using critical values and things like that. The stuff that we're doing in with our actual data analyses will generally be reporting p-values and stuff like that. So we don't often report critical values for this stuff, but in this basic hand calculation where we've gone through, say F value of 11.28 falls within critical region set at alpha 0.5 for F critical 2 and 12. Results provide support for potential effect of ambient temperature on learning in the larger student population, given that data were largely incompatible with the null hypotheses of equal performance across conditions, right? Then we've got an F value and S, a Bayes factor, right? So basically the data that we've got here, I would need to get giving me similar levels of evidence against the null hypotheses as if I were to get 9 consecutive heads on what I would otherwise call as a fair coin, right? My Bayes factor, 33.1, right? Saying that assuming equal probability of the null and alternate before we started this, we would assume best case scenario that the alternate hypothesis is about 33 times more likely than the null, right? Based on our interpretive standpoints of Bayes factor, this is getting into strong evidence, right? So even though I have a very, very small study with only 5 individuals, we would still call this strong evidence against the null hypotheses here. Okay. Questions on any of this interpretation?
Is there somewhere specific, like, where you found the p-value? Did you put it into, like, these, one of the calculators?
Oh, yeah. Yeah, that's just go to GraphPad, right?
Mm-hmm.
I go to
Okay. So that, yeah.
11.6, right? Degrees of freedom, numerator, denominator. It's all in there.
Gotcha. Okay. Sounds good.
All right. Cool. All right. Let's talk about effect size real quick, and then we'll go on break. Right. Actually, you know what? Let's do break right now. Come back at 4:10, and we'll jump into effect sizes. Move on from there. Okay. All right. We'll see you in a bit. All right, folks. How are we feeling about ANOVA stuff up to this point? Okay. Is things kind of clicking, kind of coming together with sort of the approach to this and sort of how we're thinking about these models? Pretty good. Okay. Cool. We're going to jump in and get into just the last piece of this. We'll probably get into it, maybe hopefully get through the screening here. So make sure that you have that SPSS set, or sort of, if Robert, Ali, if you guys are using SATA, sort of whatever sort of set is up there, we'll get into that once we get over or cover effect size stuff here. Okay. So, all right. Here with our one-way ANOVA, so we're going to get into a different type of effect size for our ANOVA models. Okay, up to this point we've been working with D statistics. D statistics are nice because it's giving us the magnitude of an effect across two different groups, right? And our D statistics we can interpret in terms of standard deviation differences, right? Because if I say, Natalie, if I say, hey, there's a 1.5 standard deviation difference between these two groups. Is that a big difference or a small difference?
It's really big.
Yeah, it's really big, right? So if I'm talking about things, because I know what a normal curve looks like, and I can think about things in terms of standard deviation units, and so I can sort of start to make a call on sort of whether or not that's a big thing or a small thing, right? But the problem when we get over into ANOVA is that we're working with generally more than two groups, right? And so just like we had to switch over to variance to talk about a way to sort of quantify overall differences, same thing, we have to think about our effect size a little bit differently too. And so for a one-way ANOVA, our effect size, primary effect size we'll see used in terms of interpretation is going to be our eta squared, okay? Eta squared is easy to calculate. Eta squared is just our sum of squares treatment divided by our sum of squares total. Okay. We can, and in eta squared is just going to tell us, think about, again, show of hands, who here has done regression stuff? Has anybody worked with regression analyses yet? Rachel, a little bit. Anybody else? Okay. Basically, your eta squared, it's like an R squared statistic. You can interpret eta squared as the proportion of variability in your outcome that's attributable to your grouping factor, right? So I can say condition accounts for approximately 15% of the variability, total variability of my outcome. Okay. It's a measure of association, right? Where we can go through and start to say, so this, whatever my factor is, accounts for this proportion of variability in my outcome. Judd and McClellan also talk about eta squared is interpreted as the percent reduction in error, right? So if all of the variability in the other outcome is unknown to me, I don't know why, so we have all this variability, we can interpret eta squared as the percent reduction in sort of what's unknown, sort of based on this factor. So it's just kind of taking it and flipping it around on its head, a different way to think about it. I can calculate eta squared again if someone hasn't given me. Oftentimes in published data, we don't have sum of squares treatment, sum of squares total, right? So if you're calculating your own eta squared, this is the formula you ought to be using. But if I'm looking at, say, Allie's published a paper and she didn't provide sum of squares treatment, sum of squares total, as long as she has an F statistic and a degrees of freedom, I can go through and approximate eta squared by using this formula here. So again, we will work backwards with this. Okay. My eta squared statistic, known to be positively biased, more so than other measures of effect size. And again, part of this reason is, can I have an eta squared that's less than 0? No, it's a proportion of variability, right? So if I'm going to be wrong, which way am I going to be wrong? All right, I have opportunities to be wrong in the positive direction. There's not much where I can go in the opposite direction. And so eta squared is a common. It's easy to go through and calculate. The problem is that we're concerned that, particularly in smaller samples, my eta squared is going to be positively biased. Okay, it can't be less than 0, so it's always going to be greater than 0. Even if my effect is, let's say, Riley, that I have some factor that I know based on sort of divine knowledge has no impact on my outcome, right? Am I ever going to get an eta squared that's exactly 0? It's always going to be some value that's greater than 0, right? Contributing to the positive bias, okay? And so what we have instead is a better measure of effect known as our omega squared. Omega squared, a little bit more difficult to calculate, but it's a preferable effect size to eta squared if I'm looking at balanced or nearly balanced designs. Okay, and on my omega squared is just going to be my sum of squares treatment minus k minus 1, or the number of factors minus 1, times my mean squared error over sum of squares total plus mean squared error, right? So everything you need for omega squared is in your ANOVA table. You just need to make sure that you're pulling the right figures, okay? And the idea is that our omega squared statistics provide a probably better population-based estimate. Still positively biased, but less so than eta squared. And so we don't see omega squared as reported as often, even though there's sort of a big methodological push that this is a more appropriate measure, but it's more difficult to calculate as opposed to this. I mean, it's not hard. It's just a couple more things go in. But things start to get complicated if I have largely unbalanced designs or complex designs, as we'll see when we get into factorial stuff. Okay. Other measure of effect size, and this is often what you'll see, or sometimes we'll see in the calculation of power, is an F statistic. Direct relation between eta squared and F. F is just the square root of eta over 1 minus eta squared. So we can move back and forth with this. There's a direct relation. Eta squared has a nice interpretation. It's basically like an R squared. It's a proportion of variability. In these data that's accounted for by some factor, or that's shared with some factor. F, important for the calculation of power, but not a strong interpretive sort of attachment that we can make to it. So would prefer this less in terms of providing meaningful interpretations. Interpretive standards, benchmarks, using this fairly loosely for eta squared, omega squared, small effect being something that's consistent with about 1% shared variability, medium 6% shared variability, 14 or large 14% variability. For F, 0.1, 0.25, 0.4. Again, F just having less interpretive values as eta squared. So if I have to interpret something, I'll probably just report eta because it means something that I can communicate to you that should have some meaning as opposed to F. Questions on our effect size here? Okay. And eta squared, omega squared, this is just, eta squared is more of a population-based statistic. Eta squared is just a sample statistic. So for eta squared, you say, for these data, my grouping variable or condition accounts for X proportion of variability in my outcome. Omega squared is just going to be a population-based effect. So population-based estimate for effect is 0.6, suggesting that 6% of the population variance and outcome attributable to group, condition, so on and so forth. All right. Calculation for confidence intervals around eta squared. I used to be really big on this, and less so just because eta squared, they're often quite small, and we're eta squared is generally not the effect that we're most interested in with these types of analyses. But we can go through and calculate confidence intervals around eta squared, just as we can calculate confidence intervals around D. Procedure is pretty much the same. What I'm just going to do in my non-centrality calculator is I'm going to choose an F as opposed to a T. I'm going to plug in my value, have my degrees of freedom here. Now, the one thing we want to change here is methodologists recommend a 90% confidence interval around eta squared. And this makes makes some sense, right? Because if I'm calculating a confidence interval around D, right, I can have bias in the negative direction, I have bias in the positive direction, right? So we kind of got this either balance, right? With eta squared, really we can't sort of go less than 0, so our bias is going to be positive. And so what we're essentially doing is creating a one-tailed confidence interval around eta squared. And so what we'll do is we'll request a 90% confidence interval and then just calculate this here. Okay. Once I've got my upper and lower for my non-centrality parameter, here's my lower, here's my upper. We'll just go from there. Okay. Questions about confidence intervals around eta squared? All right. So, formal assumptions of my ANOVA model. Okay. One, homogeneity of variance or homoscedasticity. This is the same assumption that we had for our independent sample t-test. We're just extending this out to more groups. So my assumption is the populations from which I've drawn my sample all have equal variance. Okay. So the variance of the population 1, variance of population 2 is equal to variance of population 3, so on and so forth. Okay, so we're just taking that homogeneity of variance assumption for independent sample t-test, expanding it out. Okay. Now, one thing to think about here is my population variance. We think about this as my error variance, because we're assuming that any variability around my group mean, right? This is my within subjects or with my within groups variability. My within groups variability is error. So you hear this referred to sometimes as homogeneity of error variance. We're just assuming that it's equal across populations. Okay. If we violate my homogeneity variance, we would refer to this as heterogeneity of variance or heteroscedasticity. This is a term used for a lot in regression types of stuff. We'll get to that at some point in the future if you're setting it on 5300 or take a regression focused course. But basically, ANOVA is just a specific case of regression. It all fits the same in, and so some of the same stuff apply here. Okay. So I'm assuming homogeneity of variance. I have a normality assumption, although this is have an error here. CJ, are you here?
Yep.
Can you shoot me an email to modify this slide? Because again, like with our group-based analyses, the assumption here isn't that scores evidence normal distribution around the mean. It has an assumption of my homogeneity or sort of distribution of sample means is normal.
Okay, yeah, sounds good.
Awesome, thanks. All right. So again, what I'm assuming here is a normal distribution. My normality, my sampling distribution, and then I'm assuming independence, right? Assuming that my observations are independent of one another, that Natalie's score doesn't depend on Ari's score, doesn't depend on Erica's score. Okay. Informal assumptions, we're assuming that we don't contain outliers. We're assuming sample size is relatively equal across groups. If we start to violate those, we start to have to sort of take in some additional considerations. Okay. So again, our assumptions here, basically the same assumptions we have with our independent sample t-test. We're just expanding this out to include more groups. All right. So what happens if we start to violate our assumptions, right? our ANOVA models are relatively robust to violations of normality, right? If I have really kind of wonky data, right? Again, it's not too bad generally, right? Generally robust so long as I have reasonably large cell sizes. My violation homogeneity variance, also not problematic, assuming that my group level scores have a similar shape, and we're assuming the ratio of the largest to smallest variance doesn't exceed about 4:1, right? And again, make sure that we're looking here at variance and not standard deviation. But I can have violation of homogeneity of variance, but so long as it doesn't exceed this kind of 4:1 general mark, right, we're probably going to be okay. Where I find that my analyses aren't robust, where I start to question whether or not the results that I've got are reasonable, interpretable, any violation of independence, right? If I have my individual observations start to be related to one another in any way or influenced by one another, then we start to have problems and we need to use a different model. If my distribution, or if my different groups have the scores on the outcome have different shapes and unequal variance, right? So group A has a strong negative skew and a whole bunch of variance, and group B has a positive skew and a little bit of variability, then we start to worry about problems there. If I've got unequal variances and unequal sample size, violations of normality and small sample size, so really where we start to become concerned about the robustness of our analyses is when we start doubling down on some of these violations. If we get a couple of these going on, that's when we start to sit back and say, okay, well, I mean, the statistics police isn't going to kick down the door and keep us from running these analyses, but we should be we should start to become concerned about the extent to which my data or my analyses are sort of have strong or are so there starts to be impact on interpretability of the analyses that I've run. So when I'm running an ANOVA model, remember that we had that Welch-Satterthwaite option in SPSS when we're running our independent sample t-tests, right? We have the equal variances not assumed line. We can go down and read through that, right? Problem is with ANOVA, we've got more than two groups, and so we have to sort of take some of a slightly different approach. Here, what we can do is we can request a Welch test. And so in situations where we have unequal variances plus unequal sample sizes, what we would do is we would request a Welch test. Here, we get a correction to our F and our degrees of freedom. But the thing to remember with any type of corrected test, none of this makes the problem go away, right? This is something that helps improve our inferences, but it doesn't make it go away. It's not like it doesn't exist, right? And so if we're finding that we have clear violations of homogeneity, that should be homogeneity, not heterogeneity. Oh no, factors contributing to violation of should be violation of homogeneity, need to be considered. So I'm seeing that group A, condition A and condition B are very different in terms of their variability. I can have statistics that correct for or help me adjust for that, but maybe the big question that should be in my mind is why am I seeing much greater variability in this group than a different group? So for clinical folks, let's say I'm running treatment A versus treatment B versus waitlist control, okay? And I'm seeing that scores in group in treatment A are much more variable than scores in treatment B, right? What implications might that have for me thinking about which treatment or intervention might be better? If I've got an intervention, do I want, in sort of my terms of my outcome, do I want more or less variability? What's that, Robert?
You want the more consistent treatment.
Yeah, right. I mean, all things being held equal, right? If I've got a treatment that provides more variable responding among people or less variable responding, assuming treatment A and treatment B both are producing similar results, I don't know, that variability, that homogeneity of variance, or that violation of homogeneity of variance starts to make me wonder if maybe the second one is the better one to use, because at least things are more consistent, right? In the first one, I might have a larger range. People might be really higher, maybe sort of very much smaller, but on average, right, I'm probably going to want the thing that has less variability, right? So thinking about not just mean level differences, but implications for variability in our data starts to become important and something that we often gets ignored. All right. So let's go through an example here. All right. So what we're doing in this example, we've got, let's say, given research suggesting greater affective and interpersonal responding to similar versus dissimilar targets, investigators are interested in the extent to which individuals from different racial ethnic background vary in their response to emotional primes featuring homogeneous actors. Okay, so again, the idea, and so anytime you're going through and working with these types of problems in the sets, think about sort of before you jump into sort of the knee-jerk reactions, jump in and start just cranking out numbers. You're going to save yourself a lot of time if you start thinking about, okay, what's the research question? Why does this make sense? Here, what we're suggesting is that for a lot of different experimental stuff, if we're looking at emotion manipulation within the context of an experimental study, one way we'll do this is we'll use film clips or something like that to sort of elicit an emotional response from the participant. But if I'm thinking carefully and I know, well, I may have some diversity in my participants, and there's research out there that suggests that we might be more responsive to people who look like us than people who don't look like us. And so maybe is this sort of an issue with if I have a diverse sample, right? Could my film stimuli that contain primarily sort of white Western folks, could I see differences in terms of the extent to which this is effective based on backgrounds of my participants, right? And so this is the question. And so for this study, what we do is we have a diverse sample of undergraduates asked to provide ratings of emotional valence and arousal in response to a humor eliciting film featuring non-white Hispanic actors, okay? So I've got a film that I say, okay, this is something that elicits amusement, but does it elicit amusement to a different degree in people from more diverse backgrounds than people who are from white non-Hispanic background because sort of the actors just kind of look like me, right? So what we're going to do is we want to state the null hypotheses, report the null in statistical notation, conduct our hypotheses test, calculate an effect size, S and Bayes factors, summarize everything together, right? So this is just the stuff that we've been doing up to this point, all right? But let's go through and start working through this set here. So I'm going to move you all off screen here. So if you open up our one-way ANOVA set, okay, so we've got a bunch of individuals here, a decent size, 99 individuals, right? And here we've got our participant number, we've got our racial ethnic code. We've got 1 for white non-Hispanic individuals, or 0 for white non-Hispanic individuals, black non-Hispanic as 1, and then this is our other category, which is never a good way to conduct this type of research, but we'll use it for the example. It's kind of our homogeneous or heterogeneous other category. Here we have our ratings of valence. Here we have our ratings of arousal. Okay. And so in terms of worksheets that we're going to be using here, for this one, this is just our screening. Okay. So what we're going to do first is I'm going to shrink this up. Okay. And what we want to do first, what do we want to do first with these data? And again, thinking about our one-way ANOVA is basically an extension of our independent sample t-test. What do we want to do first before we jump into our screening here? What do you think, Allie?
Check for, well, very first thing.
Yeah.
Probably check for missing data.
Yeah. So I go through, and I'm going to go through, check here, sort here, sort here, sort here. Oh, so that's participant number. So it doesn't look like we have any missing data here, right? So this is good. All right. So we go through, and what we want to do next, do we want to run these or look at these, screen these data all together? Nope. What do we want to do first, Rachel?
You probably want to split your file.
Yeah. Going to split my file, right? Because I want to go through, I want to take a look at sort of what the distribution of my scores look like across each one of my groups, right? So I'm going to go to data, I'm going to split file, and compare groups, and we use ethnicity as my factor variable. I'm going to hit paste. And now what I'm going to do is I'm going to go to analyze, descriptives. I'm going to look at valence and arousal, okay? Because these are my two outcomes. I want to see people sort of positive versus negative and sort of not at all excited to excited activation. I'm going to go through, take a look at that. I'm going to save standardized values as variables. I'm going to go to options. I'm going to request skew and kurtosis. I'm going to hit continue. And I paste that here. Okay. So what this is going to do is it's going to split file by my grouping variable. So make everybody their own. And then it's going to give me descriptives for valence and arousal, my two outcome variables. And then I'm going to save within group Z scores for these folks. I'm going to request skew and kurtosis. Okay. So I'll go through, run this all at once. Okay. So if I'm looking at this, all right, and maybe this is probably small on your screen. I don't know that I can zoom it in here and all. Let's see. No. Okay. Well, based on what you have on your screen. All right. Natalie, what are you seeing in terms of, first thing that impressions in terms of our data here? What are you seeing? Okay. So we're looking at our mean-based statistics, and we might be curious to kind of just get an assessment of what's going on. But for the purposes of our screener, what about this first column here? What are we seeing? Okay. So we've got an unbalanced design, right? I've got 41 individuals who have identified as white non-Hispanic. Reasonably close number of individuals who have identified as black non-Hispanic, but then I've got what appears to be a smattering of other people from who've identified as other backgrounds, right? And so I have about twice as many people in my white non-Hispanic and black non-Hispanic as my other category. So I've got an unbalanced design. So first thing I want to do is sort of recognize it looks like I have some unbalanced design, right? What about Erica, my min-max statistics? What should I be looking at here?
I guess it makes sense with the range of the data allowed.
Yep. So if I go through and take a look, it looks like my valence and arousal ratings are 0 to 9, 0 to 9. And so I go through, looks like all of this falls within bounds, right? So I can say from these data, it doesn't look like I have missing data. Doesn't look like I have any implausible values, but I do have a design that's unbalanced here, right? At least to some extent, right? So go through, and then last thing I might want to take a look at here, Allie, what are we seeing in terms of distribution here?
Looks pretty normal, or there doesn't seem to be like, I don't know, anything super problematic.
Okay, I can jump through the screen and give you a high five right now for your reframe on that. Yeah, we don't want to say that this is necessarily, things are looking relatively normal. We say that a lot, but we shouldn't. Probably the better way, not probably, the better way to think about this as it doesn't look like maybe we have anything that's overly problematic in terms of our distributions here, right? So again, if I'm looking at my skew's all less than absolute value of 0.6, right? Looks like I got some negative skew. My kurtosis, my white non-Hispanic folks, for valence is high on the high end, right? But again, I've got 40 people-ish. I mean, that's not a huge cell size, but for a group-based analysis, it's okay, right? So probably not anything. I might note, and probably would note, maybe some high levels of kurtosis here for my white non-Hispanic folks in terms of emotional valence, but probably not anything that's going to make me too upset or worried quite yet. Okay. All right. So, but always what I want to do is I want to go through and take a look at my take a look at my graphs, right? So what I'm going to do here is I'm going to just sort. I'm just going to sort this, and that's going to make sure my split file's off, because what I'm going to do now is I'm going to go analyze descriptives, and I'm going to do explore. And here I'm going to look at my valence and my arousal, and I'm going to take ethnicity, drop that in my factor list. So what it's going to do is it's going to give me different graphs for each one of my different groups. I'm going to put my subject number down here in my case label, because this is going to identify if on my box plots, if I get folks who are falling beyond 1.5 times the interquartile range, it's going to label those individuals with subject number as opposed to where they're at in the file, which will be a better thing for me to think about, right? I'm going to go to plots. I'm going to select histograms as opposed to 7-leaf, hit continue there, and I'm going to paste. Okay. So if I go to my examine, go through, run this. All right. So these are all lots of like fun statistics, but what I'm going to go down through is start to go through and take a look at my histogram. So here is emotional valence. Okay. Riley, anything you're seeing here in terms of emotional valence for my white non-Hispanic folks?
I mean, it looks pretty, well, I don't know, would you call that normal or bimodal? None of the above?
Right. I don't know. So this I think this is good, because this is how do we describe things that we're seeing here, right? Someone want to give Riley a hand? How might people describe this?
Symmetrical.
Yeah, I would say it's relatively symmetrical. So, and remember that this was the cell. These were the data that we saw some that kurtosis value of 2. Right. Remember, positive kurtosis is going to be kind of that sort of that narrow thing with the flat tails out, right? And so that's kind of what we're seeing here. Is it's relatively symmetrical. Some positive kurtosis here. Also have this. We got someone down here, and again, remember this is a funny film, right? And I can tell you these data. This is the cafe scene from When Harry Met Sally. Anybody familiar with have anybody seen the, okay, Riley knows what I'm talking about. A couple of you have seen it. Like, this is just a film clip that very, very reliably elicits humor in people, right? But it looks like we've got at least one person in this group who did not think that was funny at all, right? They rated this at a 0 or a 1, right? So this is someone who's disconnected from the distribution a little bit, maybe worth noting and recognizing that we do have some people who my manipulation might not have been completely effective with, right? So might want to make a note of that. But again, with this type of scale, 0 to 8, there's only so far that people can get out of bounds with this, right? So overall, Rachel, are we too concerned with this distribution? Probably. No. This is a low value, but with 40-some people, this isn't going to drag that mean out too much, right? So probably worth noting and thinking to ourselves, well, I've got a manipulation that's not perfect. Some people aren't reporting. Or maybe I go through and pull this file and say, oh, was this a miscode or something like that? Or this person really, maybe they got offended with this thing, right? So maybe we want to go through follow up on that, okay? Here, we've got my participants who identify as Black non-Hispanic, right? So again, kind of symmetrical. I mean, we've only got, again, 38 people. We're not going to get a really nice distribution here, but everything's at least stacked together. Not too much going on here. And now all of a sudden, what about this other category? What are we seeing here, Allie?
It's a little bit more scattered or like variable.
Yeah.
The scores that are more evenly distributed, probably because there's not a lot of people.
Yeah. So we only got about 20 people. What might cause me to be a little bit concerned about this distribution?
I mean, there's more people like at the either end.
Yeah. Yeah. What would we? Someone help us out. What would we call this distribution, or what does this distribution kind of look like? Riley, what about this one? What does this one look like?
I'm gonna go with my other answer.
Yeah, right. And so this is where this screening starts to become important, right? Thinking about what I'm doing. I've gone through, as often happens, as I say, okay, I've got decent representation of white non-Hispanic folks, and I've got decent representation of Black non-Hispanic folks in this group, but everybody else kind of got thrown into the mix, right? So I've got a heterogeneous group of individuals, and so from a statistical standpoint, I'm not too worried about this distribution, but from a conceptual standpoint, I might be, because what's my first question anytime I see a bimodal distribution? What's the possibility? Yeah, I've got more than one group, right? It's possible that I've got in this my sort of catch-all group here that I've actually got people from two different backgrounds who are responding to this film in very different ways, or at least subtly different ways. And so in the back of my mind as I proceed through this, I might want to go through and start looking more carefully on what's going on with this. Maybe it's not. Maybe this is just sort of randomly what this distribution looks like. But my concern should be, have I accidentally captured two different populations, collapsed them into one, and then I'm going to get something that's in the middle of the distribution that actually isn't super representative of much of any individual in here. Okay, and particularly with the way I've constructed this, that should be a big concern here. Okay, go through, take a look at my box plots. Looks like I'm actually getting more variability, maybe in my white non-Hispanic than my Black non-Hispanic in other groups, right? We see a higher median level here with some maybe negative skew going on. But overall, nothing falling too out of bounds, which you can't on a 0 to 9 scale. There's only so far you can get above or below, right? So nothing too much going on here. For my emotional arousal, this looks nice, right? With only 40 individuals, right? This is about as normal looking as you could possibly hope for. So that's looking okay. For my Black non-Hispanic participants, see maybe a little bit of a bimodal thing going on here, which would definitely want to make note of. Here, something that looks like a little bit of a negative skew in my other category, but again, nothing in this that's looking terribly concerning in terms of am I worried about the robustness of my test, but features of these data that I might want to take note of and think about because it's going to convey information that's important for interpretation and things. Okay. So looking at my box plots, seeing here, what's Natalie, what's maybe the takeaway message from my box plots here?
The other category looks a little skewed.
Okay.
The Black non-Hispanic group looks a little bit more variable. They're varied than the other categories.
Yeah. And particularly what category?
The white non-Hispanic.
Yeah. And so this starts to become maybe relevant for my research question, right? Because my research question is essentially one of internal validity, right? I've got a stimulus. I've got a manipulation that I'm hoping works pretty good. But my question is maybe it works pretty good. Maybe it works differently for individuals who look like the people in my target more so than the people who don't, right? Now, if I'm going through and I'm looking at my median levels, median response looks pretty similar across these three groups, right? But I'm looking at, for my white non-Hispanic participants who are watching a film stimuli that contains all white non-Hispanic individuals, Rachel, what does my variability look like for that group?
Relatively small.
Yeah, it looks pretty tight, right? And so on average, if I'm looking at my Black non-Hispanic group, I'm getting my median level of emotional arousal is the same, but the variability I'm getting is much bigger, right? And so is this a problem for my screening? No, right? There's nothing in here that's looking like it's going to be a problem in terms of can I move forward with these analyses? But in the screening process, if I'm looking carefully, there's some stuff that I might start to say, okay, this is relevant, right? It's not anything that's going to get captured in the number in an F-test, but it's helping me understand things about my data and what's going on in this paradigm that could be useful and helpful and actually directly relevant to sort of the question that I'm asking here. All right. So we've gone through, taking a look at our graphs. Those look to be okay, right? So now, last thing I'm going to do is go through and take a look at my z-scores, right? Off the bat, I'm not worried that I've got anybody who's going to be an intense outlier with this, but it's always nice to be able to put numbers to something so it's not just me saying, oh, it's fine, trust me. So what I'm going to do is I'm just going to go back up and I'm going to copy my original stuff. Paste it back down here. So again, I'm going to split file. I'm going to ask for descriptives for z-score of valence, z-score of arousal. Don't need to save anything. And then I don't need skew and kurtosis for my z-scores. I'm just going to modify this. And so you can go through and do this through the pull-down menu, or as you start to get more familiar with what's going on with this syntax, it's often easier to just do it in here. So if I go through and I run this, I get my standardized scores for each one of my outcomes. And Robert, tell me, what are we seeing in terms of my scores here?
For all of, or just all of them?
Yeah, just as a whole.
So non-Hispanic. Pretty much no evidence for extreme values of valence or arousal for the Black, non-Hispanic, and the other condition.
Okay. So really, yeah, if I'm looking at this, and it's always tricky to say no evidence. I mean, there's expected variability here, right? Really, probably with this, the thing that I'm going to hit on is I've got a low value here, right? Someone, and we already noted that this is someone who falls away from the distribution. So this is maybe someone who's worth comment, right? So if I go back, if I go back up to my data, right? And I look at, so for my valence, sort ascending, right? Here's my z-score. This is the person who had a relatively low score for valence, right? So I can see that participant number 68. This is someone who, again, identifies as white non-Hispanic, but they're reporting a really low valence score for this. It looks like either two things have happened. One, this person did not find that this amusement stimuli was very funny at all, or two, we've got an error in this entry code, right? Maybe they reported a 7 and my RA saw it as a 1 and misentered it. It would be at least something that I would want to go through and double check just to see what's going on, right? But at the end of the day, do I need to exclude this person? Is this person going to have a huge impact on my outcome? Probably not, just given the nature of the scale and the number of people I have in there, but probably someone worth taking a look at. Okay. So if I go through and take this all, and then when we run into our actual ANOVA design, we'll go through and run a test for homogeneity of variance, so that'll be done. So we'll do that next time. But again, for my one-way screening, no missing data, no evidence of problematic values. You see, I'm going to proceed with my sample of 99. Here, talking about my different distributions, giving sample sizes so I know how many people are in each sample, right? Looking at my extreme values here, reporting some stuff on there. But here, in terms of recommendations, I'm going to say, I don't know, this is just how I've set things up. Notice that we have an unbalanced design with modest sample size, low rating of valence in my white non-Hispanic group, likely violation of homogeneity of variance for arousal. We saw that a little bit in my box plot, right? Rachel identified that the variability in arousal for my white non-Hispanic folks is pretty tight versus more variable across others. When we go through and rerun these actual tests, we might suggest that there could be differences in the variability of scores across my different groups. So again, just trying to tie it all together, saying my racial ethnic groups are unbalanced within a limited number of people in my other group. Also, possible violation of homogeneity of variance for emotional arousal. This is a p-test for my Levine's test, right? Saying groups with the highest and the lowest variability in self-reported arousal are of similar size. So this is probably going to help mitigate bias, right? If I've got my highest group, my group with the highest number and the lowest number similar size, that should probably pretty much even out, right? We've got one person identifying inordinately low score in valence, but expected to have minimal impact on group mean given the size and the limited range of the scale. Recommend we look at the accuracy, validity of low valence rating for this case. Is this someone who screwed around? This is why, sort of in any type of experimental setting, want to have notes, right? So my RA can say, hey, this person was screwing around or didn't seem to be paying attention, or go through, check the hard copy, make sure that they didn't misinterpret a rating. Okay. Recommend investigators look at validity, accuracy of low valence rating. Also recommend the use of robust tests for group differences in arousal, considering possible explanations for observed and considering possible explanations for why we're seeing differences on this scale. So just kind of taking this recommendation piece, kind of tying it together. Anybody can go through and say, oh, this case is above or below this case, or things along those lines. Well, we wanted to be doing it with this summary is kind of you taking the screening, pulling it together to say, hey, these are the things that should be on our mind that we should be thinking about. Okay. All right. Questions? Feeling all right with stuff? Okay, cool. So looking forward, I'll go through and get your next sets scored. Okay. Honestly, if I'm looking at our schedule, just so you all can have a heads up on what things are likely to look like, we probably won't completely finish our multiple comparisons tests and follow-up test stuff next week. And then the following week is Thanksgiving, right? No, Thanksgiving is the 23rd, right? Yeah. Yeah, or the week of the 23rd. It's the 26th? Okay, yeah, gotcha. Okay, so in terms of thinking about your workload, what we'll probably do, so we have set 5 due on the 13th, okay? Set 6 probably won't be done until probably the 4th, okay? Just to give you guys a chance to go through, because we're going to go through and we're going to do, so we'll spend next week, we'll probably get about all the way finished with the individual or the comparison tests, right? But we probably won't make it all the way through. So what we'll do is I'll get that assignment out to you so you can start working on it. You'll have enough information to get most of it put together. So, but probably that's not going to be due until that last Friday of classes on the 4th. Our last set will be into, we'll have that due like the last Friday of, is the 4th our last day of classes or is the 11th last day of classes? What do we have?
I think
The
the 4th is
4th.
last, but then the 11th is finals week.
The 11th is finals week. And so just in terms, so our factorial ANOVA set, that'll be due, probably we'll have that due the last week of final, or the last day of finals, so the 11th. So just in terms, if that helps you game out where your projects and things like that are all going to be, you'll have these sets due or to work on with lots of time, so plenty of time to go through and do it. But just that's probably what you should be thinking about is when due dates are going to come up with stuff. Does that sound all right? Awesome. Okay, cool. What's that?
You said the 13th, 4th, and 11th, right?
Yeah, so set 5, the one that you're working on right now, that's going to be due the 13th, right? But we probably won't be all the way finished with the follow-up tests, stuff that we'll need to do by next week. It'll probably bleed into the class on the 18th is when we'll finish that up. So I don't want to have an assignment due on the 20th if we just finish things up. So, and I'm not going to have you send me anything. I mean, if you want to, right? So to get this stuff done as early as you can. I'm saying if you elect to escape from your family and work on stat homework, this is good. You'd be like, my stat professor, he's a jerk, and he lie to him and be like, oh yeah, I have something due on Friday. Go through and get that set up. But you'll have plenty of time to go through and work on this first ANOVA set, and then our last set on factorial stuff will just be due the last day of final. So I mean, you think it's not a final. I mean, it'll be cumulative in that it's sort of pulling in everything we've learned to all semesters, but it's not necessarily have any special weight or, well, actually that's not true. I think it did sort of give that double points just in case everybody's, but you guys are fine. You're doing well. So that's what we're looking at in terms of deadlines, just so you can think about where things are going to fall, plan appropriately. But as you're working through that, just let me know if you're running into questions or touch base with CJ and we'll help you out. Sound good? Okay, awesome. Good to see you guys. Let me know if you have difficulties, but it seems like you're pulling this stuff together really well. So, nice work. Thumbs up. All right, go. have a drink or sort of whatever your other vice is, as long as it's not something illegal. All right, we'll see ya.